Hello everyone, so today we're going to talk about Copenhagen interpretation. So Copenhagen interpretation is an epistemic theory of quantum mechanics which was made during 1925 and 1927 with the contribution of various scientifics like Bohr, Heisenberg, Born, Schrödinger and others, and is built axiomatically from 6 different postulates that we're going to see through this video. So the first postulate is a particular postulate that is going to define what is a wave function. And this postulate says that the state of a quantum mechanical system is completely specified by a wave function that we can call also a state function, so psi rt, that depends on the coordinate r of the particle on the time t. A wave function that has the following property in the universe. So we can see that the probability of finding the particle in the universe is always equal to 1. A condition of normalization that must be satisfied and which ensures that the particles lie in the volume element d2 at the probability that we can see in the following equation. Thus, according to this normalization condition, the wave function is first of all positive. Indeed, we can see that the probability is strictly superior to 0 whenever it is in the equation. And moreover, the wave function is single valued. For any given coordinate r and any given time, the psi wave function must always have a unique value in order to guarantee that for a given state, there is only one probability. Indeed, having more than one probability for a given state means that the system is absurd. And thirdly, the wave function must be square integrable so that it can be used as a probability density. If we take the same reasonment as the secondly, we can see that having the integral being infinite will be absurd and impossible if we want to have a probability density. And last but not least, the wave function is continuous in all first-order derivatives. Indeed, if we take the example of a discontinuous first derivative, so in it we will find an infinite momentum, which would imply an infinite second derivative in which we will find an infinite kinetic energy, which is impossible in a physical realistic system, we can deduce that the wave function is always continuous in all first-order derivatives. In a discontinuous wave function's derivative, momentum and kinetic energy aren't defined, which is totally absurd physically. So in order that they are defined, we need that it is continuous in all first-order derivatives. So now let's talk about the second postulate. So the second postulate says that to every observable in classical mechanics, there corresponds a linear emission operator in quantum mechanics. So you can see some Hermitian examples there, which I won't describe, but we can see the position, the momentum, the kinetic energy, the potential energy, the total energy, which is the sum of kinetic energy and potential energy, and the angular momentum. And all these Hermitian operators have two properties. First, their eigenvalues are real. Secondly, their eigenfunctions are orthogonal to each other, or their eigenfunctions linear combination. Then we have the third postulate of Copenhagen interpretation. So the third postulate says that in any measurement of the observable associated with the operator that are marked with the A circumflex, the only value that will ever be observed are the eigenvalue alpha that satisfies the following eigenvalue equation that you can see as follows. This is the postulate that the value of dynamical variables are quantized in quantum mechanics. Although measurements must always yield an eigenvalue. The state does not originally have to be in an eigenstate of A. An arbitrary state can be expanded in the complete set of eigenvectors of A as the sum of complex number multiplied by the psi function according to the complex number. A sum where n can run to infinity in principle. This postulate implies that measurement of A will yield one of the eigenvalue alpha with the probability of the complex number square integrable, and that Psi's measurement implies the collapse of a wave function into the corresponding alpha eigenstate of Psi. And one idea worth mentioning is that if alpha is degenerate, then the wave function collapses into a degenerate subspace. For the fourth postulate of Copenhagen interpretation, it says that for a system in a state described by the wave function Psi, the average value of the observable corresponding to A is given by the following equation. And if we take into account that the Psi function, the Psi wave function, is normalized according to the first postulate, then the probability will stay to 1, so we have the next equation as follows. The fifth postulate is pretty easy. So the fifth postulate says that the wave function of a system evolves in time according to the time-independent Schrödinger equation that we can see as follows. And last but not least, the number 6 of the postulates of Copenhagen interpretations says that the total wave function must be asymmetric with respect to the interchange of all coordinates of one fermion with those of another. Electronic speed must be included in this set of coordinates. And also, the Pauli exclusion principle is a direct result of this asymmetric postulate. And that will close our video. So to resume, the Copenhagen interpretation built axiomatically quantum mechanics in order to understand more profoundly this domain, and it is built on 6 postulates that we described through this video. Thank you very much for listening. Please subscribe and give us a thumbs up if you like it. Enjoy your day. Have fun.